Hello. So I'm going to talk about an incomplete guide to C++ object lifetimes. But before I begin, I work at ThinkCell. I'm a software engineer there. We're hiring. So we do a plugin for Microsoft PowerPoint. It's more interesting engineering than that things. Lots of reverse engineering. We sort of hack ourselves into PowerPoint. So if you're interested in that, we're hiring. So it's about object lifetimes. So what are objects and what are lifetimes? Well, this is a quote from the C++ standard. I'm on the committee, so I'm going to do that a lot. And essentially, everything you do in C++ is manipulate objects. All the C++ program does is create objects, destroy objects, and change their values. So objects are fundamental to C++. And I don't mean objects in the sense of object-oriented programming. Object is a term of art from the C++ standard. It's something that has a particular type, occupies a region of storage at a particular address, and stores a particular value there. So for example, here we have two objects. The first object is an int named x. It's currently storing the value 42. Then we create a second object named y, currently storing the float 3.14f. And then we can later change the object x. So objects are mutable. And almost everything is an object, except for two things. Functions. Functions aren't objects. Even though functions occupy physical storage in your computer, they're not considered objects. Only function pointers themselves are objects. And when you use a function, it converts to a function pointer, which is a value which can then be stored in an object. But a function on its own isn't an object. Also, references aren't objects. References are aliases to other objects. So here we're having one object x and then one alias ref. And ref is just another name for x. And they share all the same properties. So what is lifetime? Well, the lifetime of an object is just a one-time property. And it's a pretty important property. Because all other properties are only valid when you access an object during its lifetime. And in particular, there are significant restrictions on accessing an object outside its lifetime. So we have to make sure that we only use objects when they're alive. At a very high level, this is the object lifetime cycle. So the first step is we allocate storage. And the second step, we initialize an object, start its lifetime by giving it an initial value. Then we can use that object, change its value, read its value, and then we destroy that object. This ends the lifetime, and afterwards we can deallocate the storage where the object lives. It's important to point out that lifetime is something the standard invented. It's used to describe the semantics on the abstract machine. It has absolutely nothing to do with the physical machine the program is executing on. The CPU doesn't care about object lifetime. The compiler does, and the compiler will optimize accordingly, but it's a term of art. It doesn't really actually matter on the physical machine, as we will see later on. So let's begin. The talk is structured at a level. We're going to start simple and going to get more and more into the weeds. So, intro.update paragraph 1. An object is created by a definition. So here we have a definition of a variable x. This creates an object, allocates storage, starts its lifetime. We can then use the object and change its value. And when we reach the closing brace, the object is destroyed, the lifetime ends, and we deallocate the storage. Now, when exactly this happens depends on the storage duration. So the storage duration controls when the storage is allocated and deallocated. And here we have to consider three storage durations. The first one is automatic storage duration. This is the storage duration of local variables. They're allocated at the beginning of the block and deallocated at the end of the block. So when you have a local variable, it's allocated in a block, and then when the block ends, it's deallocated. Then we've got a static storage duration. This is all global variables, or function local statics. Their storage is allocated at the beginning of the program and deallocated at the end. So throughout the entire lifetime of the program, the variable has storage. And finally, that storage duration is like static, but instead of per program, it's per thread, and each object has a distinct copy per each thread. Now, that storage duration is not the same as lifetime. Storage duration just controls when the storage is allocated, but not the lifetime. And in general, this is not the same. The lifetime is a subset of the storage duration. So the lifetime only starts when both storage has been allocated and we've given it an initial value. So to answer the lifetime for variables, we have to look at when they're initialized. And the good news is for automatic storage duration, this is the same. So when we allocate storage, or more precisely, once we reach control flow of the variable declaration where we reach the storage, we also have the lifetime, and when we deallocate the storage, the lifetime ends. So that's easy. For static and thread local storage, it's much more complicated. Then we have to distinguish between function local statics and actual global variables. There's const init, there's dynamic initialization, there are techniques such as nifty counters. We have to look at the module dependency graph, inline variables, and so on. It gets really, really complicated. I gave an entire 60-minute talk just about on static initialization. So I'm not going to be covering it here, but essentially, sometime after the storage has been allocated, the program starts, your static variables are initialized in some order. Now, the initialization of an object is optional. In general, we can start the lifetime of an object without a known value. And so, when we allocate storage for an object, but no initialization is performed, for example, when we're having an int without a constructor, that object retains an indeterminate value, and when we use an expression that produces an indeterminate value, we have undefined behavior. So here, we just write int x. This allocates the storage, and because we don't perform any initialization, initialization is immediately considered complete, so the lifetime starts. We now have a valid object with an indeterminate value. So this is undefined behavior. The expression x evaluates the indeterminate value. This is undefined behavior. What we need to do is we assign it. This assignment is fine because we're having an object, and because we don't use the value, there is no undefined behavior, and then we can use it. So the lifetime starts even without initialization. We're just not allowed to use it before we give it a value. This is actually going to change in C++26. So in C++26, it is no longer undefined behavior. Instead, we're going to introduce a new term, erroneous behavior. Erroneous behavior is essentially what we wanted undefined behavior to be. The compiler isn't allowed to do arbitrary optimization, assuming that erroneous undefined behavior doesn't happen. Instead, it's only allowed to issue a diagnostic and or terminate the program. So it's a much more tame form of undefined behavior that doesn't allow any dangerous optimizations. Any questions about the lifetime of variables at this point? Good. So let's move on to new and delete. An object can also be created by a new expression. So here, we're writing new int. This creates an object, allocates storage for it, and starts the lifetime. We can then use the object as before, and then we need to delete the object, otherwise we're having a memory leak. And now that we're actually having two objects here. One is the int allocated on the heap, and then we've got a pointer to an int. This is an object that lives on the stack with automatic storage duration. It's also possible to create one with indeterminate values. So here we're allocating an object, starting its lifetime with an indeterminate value. So using it as undefined behavior, or erroneous in C++26, until we assign it. And that's actually even simpler, because with new and delete, we're having full manual control over the lifetime of an object. So let's talk about something more interesting, temporary objects. So an object can also be created when a temporary object is created, which is a tautology. So here, we're having a function that takes a constant reference, and we're invoking it with the number 42. Now, the number 42 isn't an object, and references are aliases for objects. So in order to make this code work, the compiler needs to create a temporary object for the reference to alias. The technical term for that is temporary materialization conversion, which is a great phrase for Hangman. And then we've got this beautiful sentence from the standard. A PR value of type T can be converted to an X value of type T. This conversion initializes a temporary object of type T from the PR value by evaluating the PR value with the temporary object as its result object and produces an X value denoting the temporary object. Somebody was trying to hit this word count there. What this essentially means is whenever we're using a PR value, like the number 42, in a context where we require an X value, so reference to an object, we create a temporary object. This happens as we've seen when we bind to reference to a PR value. So on const L value reference, on R value reference. When we do member access on a PR value, member functions take a this pointer. For the this pointer, we need some storage, so we need to create a temporary object. When we use an array as array PR values, arrays really want to be pointers, so we need to store the array somewhere, so we don't really have array PR values. As soon as we use them, they get turned into temporary objects. And the interesting thing is, if you've got a function that returns, for example, a std string by value, that has potentially allocated some storage, so we need to destroy it at some point to deallocate its storage. So when we just call the function, the compiler initializes a temporary object in order to call the destructor on it, which is interesting. So what's the lifetime? Well, when the temporary is created, the lifetime starts. And the lifetime ends at the last step of evaluating the full expression. So we've got a function that takes a bunch of references, and we're invoking it with two PR values. This creates two temporary objects in some order because the evaluation of function arguments is unspecified, and they're destroyed at the semicolon. Crucially, they're destroyed after the function call completes, so it's safe to use the references while we're inside the function. But it's not necessarily safe to store a pointer to them somewhere else because they might be temporaries, they might be destroyed at the semicolon. Now, there are two exceptions to this rule. They are called temporary lifetime extension. The first one is in this case. So here we're having a temporary, and we're binding it to a reference. And normally, without this exception, the temporary would be immediately destroyed at the semicolon, we're having a dangling reference. This would be a bit silly, so the standard says the lifetime is extended to match the reference. So as long as we can use the reference, the temporary is left alive. Otherwise, this would just be silly code that probably shouldn't work. Now, that you have to be really careful there. This only happens when you bind the reference directly to a temporary. So we have a function get strings, and this returns a vector of string as PR value. When we bind a reference to that, as in the first case, we're having lifetime extension because we're binding a reference to a temporary, to a PR value. But in the second case, we're calling operator square bracket. Now, operator square bracket returns a reference. So we don't get temporary lifetime extension because we're binding a reference to a reference. The compiler has created a temporary that holds the vector.string. This is then passed to the operator square bracket and return a reference. But that temporary is then destroyed at the semicolon. So we're creating a dangling reference here. Because we're not binding a reference directly to a temporary, only to some part of an existing thing. So you have to be really, really careful with temporary lifetime extension. The second case of temporary lifetime extension is in range-based for loop. So whenever the range expression, which is the thing after the colon, creates some temporary objects, their lifetime gets extended until the end of the loop. This means that it's safe to write code like this. Right? So we're iterating over all the strings that this creates temporary objects, and this will be destroyed at the end of the loop. But it's also safe to iterate over the characters of the first string, because all temporaries created in the range-based for loop live until the end of the thing. So this is a special exception to make this code like this work. So in a range-based for loop, you essentially never have to worry about the lifetime of temporary objects. They get extended. So let's talk about placement new. Because objects can be created by new expression, but there's a special kind of new expression, the so-called placement new. It allows us to explicitly call a constructor. So when we're having some memory, we can call placement new to create an object in that memory. So how do we get memory in order to do that without having objects already in it? Right? Oh, there's this. For example, we could use malloc and related allocation functions. So here we're just allocating storage, and then we're starting the lifetime using placement new. We can then use our object. We can call the destructor by calling destroy@. This destroys the object. And then we're freeing the memory. And now we've got like the full control over the manual object lifecycle, because we're doing each individual step on its own. Allocating storage, starting the lifetime, using it, ending the lifetime, and deallocating the storage. We can also use an array of unsent char.byte. So this is storage suitable aligned for an int. So we're allocating storage for it. We then can create an int in that storage. And start using it as before, need to destroy it at some point, and then the storage gets deallocated when the stack gets cleaned up. Interestingly enough, we can also reuse the memory of an existing object. So here we're having our int x. This creates an object and starts its lifetime. We then destroy it and ending the lifetime. So now we're just having storage where an object used to be. We can then reuse that storage to start the lifetime of a different object, which we're then allowed to use. And then when we destroy it, we deallocate the storage and start the lifetime of and end the lifetime as before. Now, when you do that, you have to be really careful. For example, const is const. You cannot use it to change the value of a const thing. So here we're having a const int, we're ending its lifetime, this is fine. But then we're putting a new int in its place. This is undefined behavior, because this would change const memory, and const is const. Most of the time. If you're having a const object on the heap, we're fine to do it, because const on the heap doesn't matter. It's only const in static storage duration or const in automatic storage duration. So even though we're having a const int on the heap, we're allowed to change it by reusing the storage for a different object. Also note that the compiler doesn't care what we do, it will still run the destructor. So here we're having a string, we're ending its lifetime, and then the compiler is going to end its lifetime again. So we have to be really careful to put something back before the compiler will generate the destructor code. Now, back to this example. We're having our int, we're just ending its lifetime, we're creating a new one in its place, and then we're using the pointer that we got from placement new. This is fine. Now, what about this? We've destroyed our int, we put a new int in its place, and we continue using the name of the variable. is this okay? Well, the standard says this is okay as long as the object is transparently replaced. So the definition is that A is transparently replaceable by B if A and B use the same storage, and A and B have the same type, ignoring CV qualifiers. And then there are some exceptions for const objects, base classes, and non-unique address members. And then when you deal with sub-objects, you have to recursively go to the parent object, but that's not important right here. So this is a transparent replacement because we're creating an object of the same type at the same storage, and we're allowed to reuse the old name even though we sort of changed what it means. Right? We're starting one object, destroying it, creating a new one at the same place, and then just using their old name. This is fine. This, however, is not fine. So now we're having a const object on the heap. We are allowed to replace it, and then we're allowed to use the pointer. But we're not allowed to use the old pointer because const objects cannot be transparently replaced. And this isn't fine because the idea is the compiler sees, okay, the pointer points to a constant. That can never change. So I'm not going to bother and reload the value in the second dereference because it's a pointer to a constant that can't change. Right? So this is undefined behavior because we sort of changed the thing even though the compiler doesn't necessarily want to track it. Now we can fix that by using std_launder. Std_launder is a magic identity function. It takes a pointer and returns a pointer, but it magically makes it okay. So when we launder our pointer, we're now allowed to dereference it. Because the launder pointer, this sort of indicates to the compiler, hey, this might have changed, please reload it. Note that even though std_launder exists and has this property here, it's not like a magic thing against undefined behavior. So if we assume that like a float and an int have the same type, size and alignment, when we create a float and we destroy it, we can create a new int in its place. This is fine, but this is non-transparent. So we can dereference the pointer because we're having a pointer to an int object that we just created. But we can no longer dereference the pointer to the float because we don't have a float, right? We've destroyed it and put an int in its place. We don't have a float. And even if we launder it, like we still don't have a float, right? Launder is not just a magic thing that makes you get rid of undefined behavior. It's just used in this very particular use case. Questions about this? Okay. So let's talk about implicit object creation. An object is created by an operation that implicitly creates objects. Great. What does it mean? The idea is the following C-like C++ code. We're using malloc to allocate an int. And then we're just using it. This should not be undefined behavior because this is sort of C-style code that people write. But why is but with everything I've shown you, this is undefined behavior because we don't have an int object. We've just allocated storage. So we shouldn't be allowed to assign a value to it because we don't have an int object. So how does this get fixed? Because we don't want this to be undefined behavior. Well, essentially there are some operation that implicitly creates objects, and those operations just create objects if doing so would result in the program having no undefined behavior. So essentially, the compiler helps you to avoid undefined behavior. This is like the only instance where the compiler is actually on your side and prevents undefined behavior by implicitly creating objects for you. It only does that for implicit lifetime types. This is the definition. But in a nutshell, it's types where the constructor and the destructor do nothing. If they are side effects, the compiler cannot just call them for you. Right? So if you're having a plain int or a trivial type, the compiler, it's an implicit lifetime type, and the compiler will help you. So when does the compiler help you? Whenever you're calling any sort of allocation function, malloc, operator new, allocator allocate, and so on. The compiler will implicitly create an int object for you to make this code well-formed. Thank you. Similarly, whenever you have an unsigned char buffer, the compiler will implicitly create objects in there. So here we're having a buffer, we're just treating it as an int pointer, and then start using it. The compiler will implicitly create an int object in that buffer to make the code well-formed. Except in principle, this actually has undefined behavior due to a bug in the standard. So even though the compiler will create an int for you, you don't actually get a pointer to that int when you reinterpret cast it. You're still having a pointer to the array and not to the int inside. So you have to use launder to fix it, but this is a bug in the standard. There's a proposal for it. There's just some sentence missing in the standard. This will be well-formed, so just pretend the launder isn't there. It's going to be fixed. There are a lot of bugs in the standard in this area. It's incredible. memcopy and memmove also implicitly create objects. So here we're having a char array. A char array on its own does not implicitly create objects, only unsigned char and std byte. But when we memcopy some bytes in there, and then use it as an int, this will implicitly create an int in order to make those well-formed. And again, the launder is because of the bug in the standard. Pretend this doesn't exist. So the compiler, the memcopy implicitly creates an int because we need an int. And finally, the implementation is allowed to add own functions that implicitly create objects, probably stuff like mmap or virtual alloc. Right? So if you mmap a file, the compiler will implicitly create objects in there, so it can just start reading the data. Now, how does the compiler know which objects to create in there? Well, the answer is easy. It uses time travel. So here we have a buffer that can fit both a float or an int. And then we roll the dice, and depending on the dice roll, we either create an int, use it as an int, or use it as a float. So when the compiler allocates a storage, it doesn't know whether it needs to put an int or float in there. When control flow continues and we reach the reinterpret cast, the compiler knows, this must have been an int. So the compiler travels back in time to create an int as the point of the allocation of the buffer. And it really is time travel, because the reinterpret cast doesn't do it. The allocation of the buffer does it. So the compiler has to use time travel to do that. Alternatively, you could see it like quantum mechanics, so it creates like an int or a float at the same time, and then the wave function collapses once you use it. And importantly, like, okay, so let's say we rolled the dice so that we needed an int. The compiler has created an int in there using time travel. But afterwards, we cannot use it as a float. The compiler will not do it again. The buffer contains an int. The buffer has always contained an int. And it will not just put a float in there afterwards, once it's decided it's an int. And also, this is why it's like the constructor cannot have side effects. Because I've been told that time travel isn't actually implementable in a compiler, so it can't just go back in time to execute side effects as soon as you need them. So, and this is also why I meant lifetime is a thing on the abstract machine. It has nothing to do with your CPU, right? This is a term of art to make it well-formed, and in order to make this possible, like, we need to use time travel. And again, implicit object creation does not prevent undefined behavior. So here we're having an int, we're reinterpret casting as a float. This is still undefined behavior. The compiler will not implicitly create a float for us, right? It only happens in very narrow use cases and not in everything else. So code like this is really common. Let's say you're communicating over a network, and one side directly puts a struct on the network, and then the other side just wants to read it, right? So we can get our buffer from the network, and we just reinterpret cast it as our struct and start reading it. Depending on how we got the bytes, this might be undefined behavior. Because only if the bytes came from one of those magic operations that implicitly create objects will the compiler travel back in time to implicitly create the data object. But if it doesn't, this is undefined behavior. It's really common, and like before C++20, there was no way to make it not undefined without performance guarantees. So the compiler doesn't really care that's undefined behavior, but technically it's still undefined behavior. So how do we fix it? How do we ensure that we've got a data object in our buffer? Well, we could use placement new. Right? This creates an object in the buffer. The problem is, this starts the lifetime of a brand new object at this point in time. And even though the type is trivial, and the constructor doesn't actually change the bytes, we don't have any guarantee that this doesn't touch the bytes, right? Because like the compiler could say, okay, in debug mode, I'm gonna zero initialize everything in placement. Right? So semantically, this creates a new object that overrides the old one. Whatever's in there, this might change the bytes. So while this is not undefined behavior, it also might not give the correct data, which is worse. The correct way is to use start lifetime as. Start lifetime as is like a reinterpret cast. You give it an address, you give it a type, it returns a pointer to a type, but while doing so, it implicitly creates objects in that storage, crucially without overwriting the bytes. So this is a guaranteed way to tell to the compiler, hey, I've got a buffer, I need a data object in there. Please create a data object in there and don't touch the bytes. Right? So if you're writing code like this, once I think start lifetime as in C++23 or something, you can use that function to make your code well-formed. The implementation of start lifetime as is a compiler built-in, like it boils down to reinterpret cast, but you can actually write it your own in standard code by using a memmove of pointer of size of t. Right? This copies the bytes to itself, which doesn't do anything, but because memmove implicitly creates objects, right, you have implicitly created an object. But you should use start lifetime as instead, works also with const memory and stuff like that. So, similar to implicit creation, we're also having implicit destruction. So an object lifetime ends when we destroy the object by calling its destructor, but also when we release or reuse the storage. So when we want to reuse the storage, we can just call placement new. Right? We don't have to call destroy at. This implicitly ends the lifetime of the first int object and starts the lifetime of a new int object. And then it's fine. Similarly, when we have an unsigned char buffer, this actually starts the lifetime of an unsigned char array. Right? And then when we call placement new, we end the lifetime of the unsigned char array and start the lifetime of the int. So just by reusing storage, we implicitly create objects. As a consequence, memory leaks aren't actually undefined behavior. So if we're having a string, this needs to allocate memory, and then we just placement new in a different string in there. This destroys, ends the lifetime of the first string object without running the destructor. This leaks the memory, but it's not undefined behavior. It's just a memory leak. Memory leaks are fine, right? But for the standard, semantically speaking. Okay. So I will end this talk by talking about provenance. Unless other questions about.
Sorry, yes.
Yes.
When you did the start as lifetime, was it legal if the constructor had side effects or not? Probably not.
So start lifetime s. The question is, can the constructor have side effects for start lifetime s? Just with everything else, start lifetime s requires an implicit lifetime type, so the constructor must not have side effects. Okay. So let's talk about provenance. Consider this code. We're having two variables x and y. We're setting y to 11. Then we're doing something with the address of x, and then we return y. We expect the compiler to optimize the return y to return 11, because y is set to 11, and then we're not changing it. But what the definition of do something looks like that? So do something takes the pointer, goes one further, and sets it to 42. And let's say it just so happens that that is the address of y. So the stack is just set up in such a way that like y lives an address of x plus 1. Then this optimization would be invalid because we're changing y. But you say, okay, this is undefined behavior, right? We don't have any guarantee that this works. Okay? What about this? So if the address of x plus 1 is the address of y, we're calling do something with the address of x and setting it to 42. This clearly sets y, right? Whenever we call do something, we're changing y, because this is the same address of y. So is the compiler still allowed to optimize that to return 11? Right? The compiler really wants to optimize to return to 11, because otherwise it has to look at like every single function in your program in order to justify the optimization. So the standard would very like for this optimization to take place, which means this code is undefined behavior. But how can it be undefined behavior? Like the address of x plus 1 is the address of y. Well, just because two pointers are equal doesn't mean they point to the same object. Right? Just because they physically store the same exact bits doesn't mean they can be used interchangeable to point to the same object. This has something to do with provenance. So a pointer is logically a pair. It has a physical address and it has a provenance. The address is the only thing that's actually stored in memory that happens at runtime. This is the thing the pointer points to. And then the provenance sort of remembers how you obtained that address. The allocation the pointer was derived from. And the pointer dereference is only valid if the address is in the range of the allowed addresses for the provenances, and the current provenance at that address still matches the provenance of the pointer. And crucially, pointer arithmetic never changes provenance. So in this code, even though the address of x plus 1 might be the same as the address of y, they have different provenances. Like the pointer still has the provenance of x, not the provenance of y. And so when we do the pointer arithmetic, we cannot dereference it because the provenance does not match of that address. And this is the reason the optimization is justified. Because pointers aren't interchangeable just because the addresses are the same. They also need to have the same provenance. And we can also use it to understand std launder. So here we're creating a const object in the heap. This is provenance A. We're then destroying it. We're then creating a new object. This is provenance B. We're allowed to use the new pointer because it has the correct provenance, but we're not allowed to use the old pointer because it has the wrong provenance. And when we use std launder updates the provenance. It doesn't change the address, which makes it an identity function, but it magically updates the provenance to match the provenance at that memory location. So by using std launder, we can update the provenance to make it well-formed. So every object has unique provenance. Objects in an array all have the same provenance. This allows us to do pointer arithmetic to get from one object in the array to the next object in the array. And when you reuse the memory and you're not doing transparent replacement, then this changes the provenance. And then you have to use std_launder to update the provenance of an object. But crucially, std_launder cannot be used in the first case. So we cannot say std_launder pointer +1 to update y, because one precondition of std_launder is that you would be allowed to dereference the object in the first place if you had the valid thing there. And the past the end pointer is never dereferenceable, so we cannot use it to fix via std_launder. Okay, and with that, I'm done. It seems I could have left some more slides in. I've shortened it from a 90-minute talk. So I will end with some personal guidelines. Don't rely on implicit object creation. It's a bit weird magic time travel. Instead, use placement new when you explicitly want to create a new object. So when you're mallocing something, use placement new to create the int instead of just assignment. And use start lifetime as. Right? When you just want to start the lifetime of object without changing the bytes, write that. Right? Write start lifetime as, makes it way more explicit what's going on. Whenever possible, use the pointer return from placement new and start lifetime as, because that pointer has always the correct provenance. Then you don't have to worry about transparent replacement. You don't have to worry about launder. You can just use the pointer. Don't worry about any of that. This is not always possible. It might sometimes mean that you need to store like an extra pointer in your class that points to the same memory but with the correct provenance. Then go ahead and use std_launder. But in many cases, when you can, just use the pointer directly. And while you can create objects in an unsigned char buffer, just use a union to sort of delay construction of an object. This is much nicer. You don't have to worry about reinterpret casts, provenance issues, and so on. It's just simpler to reason about. And with that, I'm done. Once again, we're hiring. I've got some nice think cell socks I can hand out if you're interested. They're L value, R value socks. And again, like this is a short version. You can find the full slides of the 90-minute version where I go into a lot more details and a lot more bugs in the C++ standard at my website. There's so much broken code in there. It's incredible. Thank you.
Brilliant talk. Thank you very much.
You're welcome. Yeah.
So not doing too much with C++. What is the motivation for provenance in the first place?
Yeah, so the motivation for provenance is essentially to like allow this optimization, right?
Okay.
We want the compiler would just like to optimize each function by looking at it in isolation.
Okay.
And it looks at it and sees, okay, the address of y doesn't escape the function, so we can optimize the assignment. And without provenance, like it cannot do a lot of very basic optimization, right? Because it sort of has to assume that like everything can change all memory, which would break so many optimizations. Like provenance is really there for compiler optimizations.
A lot of the stud calls, this is all 20 and 23, a lot of newer stuff.
Yeah. So the implicit lifetime thing and the implicit object creation didn't exist before C++ 20. So like lots of code was technically undefined behavior because it was just a big hole in the model until somebody noticed and like fixed the wording. So the intent was really to make what people write well-formed. And then there was this edge case where like you just got the pointer, you don't know where it came from, and then you can use the start lifetime as to ensure that you're in this very basic thing. Yes. So the implicit object creation is in 20, start lifetime as is in 23. But again, like compilers are not going to punish you for it because you had no way to write it legally before C++ 20. Similar to std_launder.
I'm still on 14.
Yeah. std_launder 17. Yeah, it's pretty fun. Like before C++ 17, there was no way to write std vector in standard C++ without undefined behavior. It's just so much. Like, yeah.
I was a full-time C++ developer until 1999. Is there a good route to getting back up to speed, or should I just start again from scratch?
Is there a good route to get up to speed to modern C++? There is the book series by Bjarne Strustrup, A Tour of C++. I think a new edition came out. It just gives a quick overview of all features, right? So you can start picking and then just do whatever.
It's a good high-level book.
Yeah.
Cool.
Yes. Bjarne Strustrup, like the designer of C++. Yeah. Okay.
Thank you very much.
Thank you.